wamune bw'osomeseza omwana wo mu masomero ga Giant Schools omuli kampasi y'Ebombo Kalule n'ey'e Kabalagala tobona bweraliikirivu bwonna olw'omusingi okutambuzibwa ebyenjigiriza n'ensoma y'abayizi ey'omulembe. Mu masomero gaffe gano gonna tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuuka ku siniya ey'omukaaga, nga tusomesa abaana okuviira ddala ku mutendero gwa kindergarten okutuuka ku kibiina eky'omusanvu. Tulina abasomesa abakugu mu kubangula abaana n'okubateekateeka. Ebibiina abaana mwe basomera eby'omulembe omuli buli kimu ekikwata ku ebyo bye basoma, ebisuula ebyazimbibwa obulungi, ebigazi ate nga biyonjo. Okumanya ebisingawo tukubire ku nnamba z'essimu ez'owammanga.
Good morning, dear viewers. Thank you for tuning in to study biology with me. Once again, my name is Jovia Katwaise, and I'm your teacher for biology today. Just as I promised the last time, that today we are going to finalize on transport as a topic, and we are going to finalize with studying about the rate of transpiration. And then I also left behind my email for you people to write the prospected topic that we can start on the next time I'm coming back here. And the majority of you really had to email me. I saw your emails. One thing I can comment about your emails is some of us do not know the topics we study in biology. Someone emails you and says, Madam, I think we can study about the human skeleton. The human skeleton is not a topic. It's not. The topic is local support and locomotion. Or maybe someone talks about, we study about the eye. The eye is not a topic. It's just a small subsection in a topic we call coordination. And then someone talks about, you just bring about smaller hints on what, on a particular topic, but then we have to know the different topics there are in our subject if we have that much passion about it. So the majority of the students picked coordination as a topic. Actually, almost the majority. It was coordination, homeostasis and excretion, and then locomotion. Those were the major topics that were listed. Definitely, I had people who were talking about reproduction, cell division, but they were a little bit fewer compared to these other three topics I've mentioned. So the next time I'm coming back here, that is next week, if God gives me the chance to be here, we shall be starting on coordination. Purposely, we shall start on coordination in animals, and then coordination in plants will come last, because that is the major emphasis. From most of you, it was coordination in animals. So I'll start with that particular part, and then we progress well. Today, as I said, the topic is still we're going to look at rate of transpiration. That is my email there on your screen. The expectations of the lessons. What should we expect today? We expect to basically look at experiments on transpiration. The first experiment to show that transpiration occurs majorly in leaves. Then the second experiment we shall look at is an experiment to compare transpiration on the upper and the lower surface of the leaf. The next experiment we shall look at is the experiment to measure the rate of transpiration using a potometer. And then we shall sum our lesson with the adaptations of xerophytes. Xerophytes, or desert plants, to reducing the rate of transpiration. So those are the expectations of the lesson today. And then there are reference questions for the day. We have a lot of questions on transpiration. Apparently, I think UNEP loves setting about transpiration a lot, because it's a topic that most students don't understand best. So I have a lot of questions on transpiration, but purposely today I only pulled out 2 questions. The first question that will summarize today's lesson is UNEP 2014 paper 1, question number 35. The second question will be question number 36, UNEP 2008, paper 1. But if you have a UNEP book bank for biology, there are very many questions about transpiration, a lot of questions. Almost every year, something comes on transpiration or transport in plants. The textbook I used was Jeff Howard, 2000 edition, Macmillan Secondary Biology. So those are the references for today. Back to our lesson. I said we are going to look at basically experiments today, and we are starting with the experiment to show that transpiration occurs majorly in leaves. I'd request the producer to post some of those experiments on our screens, because I am not going to draw them for you, but I have them already prepared for you. On the experiment to show that transpiration occurs majorly in leaves and not in stems. The next experiment. Yeah, that one should be posted on the screens. So, in an experiment to show that transpiration occurs majorly in leaves and not in stems, remember I said when we are attempting a question on experiment, the first thing we have to do is our attempt must have a title. Then you must also have requirements or materials. Then we must have the procedure. Under the procedure, you can have your illustration under the procedure, and then you have the observation. Under the observation, you can as well have your conclusion. Kindly post the experiment we talked about onto the screens of the students. That one should be posted on the screens. And then lastly, we have the conclusion. So this experiment you're seeing on your screen is to prove that transpiration majorly occurs in leaves, in leaves and not any other part of the plant. When you look at it keenly, you're seeing a leafy tree or a leafy twig that is enclosed in a plastic bag, a dry plastic bag, or what we can call our transparent polythene bag. That is the first branch with leaves, and then the second is having branch with leaves removed. So after they get two leafy twigs. On one twig, they enclose a branch having leaves in a dry polythene bag, and then on the second branch, they remove all the leaves, and they remain with only the stem without leaves, and then still they enclose it also in a dry polythene plastic bag or polythene bag. And then they leave the experiments to stand for 4 hours in sunlight. And then after 4 hours, they come and make the observations. As you can see, after 4 hours, the leafy twig, the branch with leaves that was enclosed in a dry plastic bag or cavera, is having some droplets of water in it. As you are seeing inside, there's some kind of sweating that has taken place in that branch with leaves, and then in the other branch with leaves removed, the polythene bag remains dry. You don't find any other water droplets surrounding the inner surface of the polythene bag or the dry plastic bag, so it is dry. So that one shows that where does the water come from? The water is coming from from the branch that is having leaves than from the branch that is not having leaves. And that, to scientists, concludes that the branch that is having leaves, it's the leaves that are responsible of these water droplets that are found in the dry plastic bag after 4 hours than in the other branch that never had leaves. And that one proves that these leaves are losing water from them in form of vapor that later on settles on the surface of the polythene bag as water droplets. And when these water droplets are tested using the blue cobalt 2 chloride paper, the cobalt 2 chloride paper turns pink, showing that it's real proof that it's water. Or if they use white anhydrous copper 2 sulfate, it turns blue, showing that the droplets in the plastic bag that is enclosed on a leafy twig or in a branch with leaves are water. And then the one that is enclosing a twig with no leaves, there's no anything like water coming out. And that is a proof that transpiration majorly takes place through leaves than any other part of the plant. I remember when last week when I was here, I told you we have 3 basic types of transpiration, and that is cuticular transpiration, lenticular transpiration, and stomatotranspiration. But I remember telling you that stomatotranspiration takes the 80% of transpiration. So the highest amount of water that is lost from the plant in form of water vapor to the atmosphere is from the stomaters, of which the stomaters are always located on the leaves. So that is why you're seeing in these 2 experiments, the branch with leaves is having a lot of water lost from it into the polythene bag, and the branch without leaves is not having any water lost from it to the polythene bag, showing that transpiration majorly occurs in leaves of a plant rather than any other part of a plant or the stem. So that is the experiment in most cases we use when we are comparing, when we are to prove that transpiration happens or occurs majorly in leaves than any other part of a plant. In the normal setting, the second experiment always serves as our control experiment, whereby for it you put there the polythene bag to show if you don't find any water in that polythene bag, then shows that honestly the first experiment with leaves is a true experiment and water is coming out of the leaves. So that is the experiment to show that transpiration majorly occurs through the leaves. So if we are to attempt that question in the INEB format, assuming it's a section C number, and the question says describe an experiment to show that transpiration occurs majorly in leaves. How do you attempt it? First, you've got to state your title. The title will be an experiment to show that transpiration occurs majorly in leaves. After that, you state your requirements. What did we use in that experiment? When you saw them on the screen, kindly post them again back on the screen for people to see. As you're seeing on the screen, we need a leafy twig or a plant with leaves. And then we also need a dry polythene bag or plastic bag or dry white cavera, colorless cavera, where you can see through the water droplets. Then you also need a leafless twig or a plant with no leaves. Then we shall also need copper 2 sulfate or cobalt 2 chloride. So those are our requirements. A leafy twig, a leafless twig, or you can use a dry stick or a plant where the branch where the leaves have been removed. Then we need a plastic bag or transparent. You should specify a transparent plastic bag or transparent polythene bag. And then we also need copper 2 sulfate to prove that the droplets that we find in the leafy twig are water. So those are the requirements. And then the procedure is as you're seeing on your screens how the 2 setups are. So you tell the examiner, you get a leafy twig with a branch that is having leaves. Obtain a transparent polythene bag. Cover it around the branch containing, possessing the leaves, and tie that polythene bag with a rubber band at the end. And then you tell the examiner, get another leafy twig, remove all the leaves from a particular branch, and then uncover the leafless branch with another another transparent polythene bag, tie it with a rubber band. Then leave the experiment in sunlight to stand for 4 hours. As simple as that. Then you can make your illustrations. You don't need to cram this. You just need to know your illustrations, that this is what. This is how it should be. And from your illustration, you can derive the procedure, just like I've done. You don't need to cram everything in notes from step 1, because some teachers will give you step 1, step 2, step 3, up to around step 10. No, 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 no. You just have to write exactly what is going to be on your illustration. So simple, so easy, but with science and sense, and it will be marked correctly. And then you draw your setup as you're seeing on the screens, or you could use potted plants. You could use a plant in a pot with leaves and a plant in a pot whose leaves have been scraped off, or you can use a dry stick instead of the leafless branch. You draw them as your illustration. Then after, you come to observation. Under observation, you write what you have put in your illustration. Why did you put water droplets in a leafy twig, in a branch with leaves and no water droplets? So that is the observation, that after 4 hours, the leafy twig or the plant that has a branch with leaves covered in a transparent polythene bag will be observed to have water droplets on the surface of the polythene bag. Whereas the other one will actually not water droplets, it's liquid, not water, because we have not yet confirmed that it's water. So we'll find that it will have droplets of liquid on the surface of its polythene bag, whereas the one that was covered with a transparent polythene bag but without leaves was found to be dry as initial. No liquid droplets were obtained. And then you go on to tell the examiner, when the liquid droplets are tasted using anhydrous copper 2 sulfate, white anhydrous copper 2 sulfate, it turns to blue. Or if you decide to use cobalt 2 chloride, you tell the examiner it turns pink, proving that that is water that is on the surface of the transparent polythene bag. And what is your conclusion? Transpiration occurs majorly in leaves of a plant rather than any other part of the plant. So that was our first objective of the lesson, and I guess we are at the same pace. So the second objective of the lesson, we said we are going to look at an experiment to compare the rate of transpiration on the upper and the lower surface of the leaf. I request the producer again to post that experiment on your screen. An experiment, the next experiment is to compare the rate of transpiration on the upper and the lower surface of the leaf. I got that experiment. Kindly post it on people's screens. The next one, that one should be posted on screens. So that is the experiment. There we get one leaf, and then this leaf must be intact on a plant. Please, here they have just tried to bring out the leaf to show you exactly what is happening. But when you're getting that leaf, you get the leaves when they are intact on a plant. So when they're intact on a plant, you get a piece of blue cobalt chloride paper, and you tie the blue cobalt chloride paper on the upper side of the leaf and even at the lower side of the leaf. Now here you're seeing on the first leaf where we're having the blue cobalt chloride paper, it's basically on the upper surface of the leaf. Then there is an arrow showing you cobalt chloride paper on lower surface. So we are assuming that these two papers are both on the upper surface of the leaf and the lower surface of the leaf. Then you leave the experiment, that plant, to stand in sunlight for close to 3 hours or close to 4 hours. But you keep on checking the leaf at intervals. Say you could check the leaf at intervals of 10 minutes. And you keep on checking the color change of the cobalt chloride paper, because here we are sure that the leaf is going to lose water in form of water vapor to the atmosphere. And we want to see which of the surfaces is going to lose water first than the other. And then we also want to prove which of the surfaces is going to lose a lot of water than the other. So that is why we tie the cobalt 2 chloride paper on the upper surface of the leaf and even on the lower surface of the leaf, because we are comparing the upper and the lower surface of the leaf. Remember, I said the leaf should be from a plant that is in a potted plant, so it should not be plucked off. If you pluck it off and present it and you do it the way you do it's right now here, the experiment won't come out as expected, because the leaf must be on a potted plant and the normal conditions of growth are taking place, and the plant is taking up water and losing out water. So what happens after 3 hours, but after checking at intervals of 10 minutes. The first thing is you'll find that the cobalt chloride paper, the blue cobalt chloride paper, would turn pink, pale pink, faster at the upper surface than the lower surface, as you're seeing in the second experiment. The first cobalt chloride paper to turn pink will be that one tied on the upper surface than the lower surface. But after the 3 hours, the cobalt chloride paper on the upper surface would turn less pink, whereas that one on the lower surface would turn more pink or more intense pink in color, as you're seeing in the second experiment, in the second leaf. So why does the cobalt chloride paper turn pink faster at the upper surface than the lower surface? And why is it that after 3 hours, the lower surface will have the cobalt chloride paper turn more pink, whereas that one on the upper surface turn less pink? So that one is looking at the rate of water loss from the two surfaces of the leaf. If the cobalt chloride paper turns pink faster at the upper surface than the lower surface, it shows that the upper surface of the leaf is going to lose water faster by transpiration to the external environment than the lower surface, before the lower surface is losing. But then why does it turn less pink at the end of 3 hours and the other one turns more intense pink at the end of 3 hours? It will show that whereas the upper surface lost water faster, it lost less water in the 3 hour period. Whereas the lower surface took longer to lose water to the external environment, but it lost a lot of water at the end of the 3 hour time we've given the plant or the leaf. So what does that show? It shows that the rate of transpiration is faster at the upper surface of the leaf, and it's slower. It's slower on the lower surface of the leaf. But again, it shows that the rate of transpiration is very high at the lower surface of the leaf, and it is slower at the upper surface of the leaf. So why is it like that way? One, why do we have a faster rate of transpiration on the upper surface of the leaf? Why the cobalt chloride paper at the upper surface of the leaf turns pink faster than the lower surface? It shows that the upper surface of the leaf is always exposed to sunlight directly. There's direct sunlight intercept to it, so water in it, in the upper surface, will easily turn into water vapor because there is more latent heat at the upper surface than the lower surface. So water will easily turn into vapor and can easily escape faster than when the lower surface. That means that it takes a longer time for sunlight to reach the lower surface of the leaf than the upper surface of the leaf. And as such, the upper surface of the leaf will lose water faster by evaporation to the external environment than the lower surface of the leaf. That is why the cobalt chloride paper turns pink faster at the upper surface than the lower surface. But then, at the end of the 3 hours, the cobalt chloride paper at the upper surface turns less pink. It is pale, whereas the one that is at the lower surface turns more pink. So the intensity of the pinkness of the cobalt chloride paper now shows how the amount of water each of the two surfaces are losing. It shows that the upper surface is losing less water compared to the lower surface in a long run. What does that mean? It means that the upper surface of the leaf naturally, in most plants that are living on land, terrestrial plants, most of the terrestrial plants, the number of stomaters on the upper surface of the leaf are always lower than the number of stomaters on the lower surface of the leaf. And as such, we all know that the transpiration you're looking at here is stomatotranspiration, where water is being lost out of the leaf via the stomaters. So because the upper surface is having fewer stomaters, it may lose water fast, yes, but it's going to lose less water because of the fewer stomaters or because of the fewer outlets of the water out of the leaf. So the surface area for water loss at the upper surface of the leaf is reduced or is lower compared to the lower surface of the leaf. The lower surface of the leaf, being that it's always hidden away from direct sunlight, most stomaters will always be located at the lower surface of the leaf, in the event reduce the rate of transpiration of terrestrial plants. And because the lower surface of the leaf has very many stomaters on it, it will possess a high surface area over which it's going to lose water to the external environment by transpiration. And so at the end of the day, whereas it will not lose water faster than the upper surface of the leaf, within the interval of 3 hours, it will keep on losing a lot of water because of the more outlets of water from it to the external environment. So that is why you find that the cobalt chloride paper at the end of 3 hours, it is intense pink at the bottom of the leaf and it is pale pink at the top of the leaf. So what does that mean? That the lower surface of the leaf has the highest rate of transpiration compared to the upper surface of the leaf. This is an experiment that most students fail, by the way, because we always know that always the rate of transpiration is higher at the upper surface of the leaf because anyway, the upper surface of the leaf is in direct intercept with sunlight. It's always close to sunlight, so sunlight hits it first. Yes. The water is lost faster in the upper surface of the leaf, but less water is lost from the upper surface of the leaf because of the fewer stomaters located there, because due to lowering the rate of transpiration as an adaptation of all land plants. And then at the lower surface of the leaf, it may take longer for it to lose water to the external environment because by the time light hits the upper surface, then penetrates to the lower, it takes a longer time. But then because there are many stomaters at the lower surface of the leaf, more water is going to be lost from the lower side than the upper side. That is why the cobalt chloride paper at the lower side turns more pink. So when you look at that, the arrow is coming out showing the cobalt chloride paper from the bottom of the leaf turns more intense pink. And that is an experiment we use to compare transpiration from the upper and the lower surface. In this, examiners can also generate data on this experiment. And then they say, maybe in an experiment to investigate the rate of transpiration from the upper and the lower surface of the leaf, the following amounts of water were lost within intervals of 10 minutes. And then they create a table for time, 0 minute, 10, 20, 30, 40, 50, up to 60. And then they also show the amount of water lost from the upper surface and the amount of water lost from the lower surface. And then they tell you to plot a graph showing a relationship between time and the amount of water lost from the upper and the lower surface. When you plot a graph, the graph will come out with two lines, curves. So this will be time, say in minutes. And then this will be amount of water or rate of transpiration. So you will have two curves coming out. One curve will be showing rate of transpiration from the upper surface of the leaf. It is always higher at the start. It starts higher, but then it is lower. So this is the upper leaf surface. And then the second one will show rate of transpiration at the lower surface of the leaf. It is always lower. It starts lower than the upper because this one loses water faster than the lower surface, but it will come and then it will exceed, say like that. And this will be the lower leaf. So what does that mean? That it means that on your curve, on your graph, you'll have two line graphs. Are they line graphs? They are curves. You have two curves, but one curve will be higher than the other curve, showing that the lower leaf surface has a higher rate of transpiration than the upper leaf surface. But at the start, the upper leaf surface shows to have a higher rate of water loss compared to the lower leaf surface because I said the upper leaf is in direct intercept with sunlight, so it easily loses water than the lower leaf surface because light and heat strikes the upper surface faster and more than the lower surface. But with time, the lower surface will lose more water because there are more stomaters at the bottom than at the top. So your curves will come out in this way. And then they'll ask you, say, to describe the shape of the curves. And maybe then they'll ask you questions on transpiration. And this will take a total of 20 marks. Simple. 20 marks, but you just play around with the knowledge of transpiration that you have studied in class. So this is simple, but you need to understand the concept. If you don't understand the concept, it becomes very hard and complicated. But if you understand the concept, it is the simplest you can ever do. So that is the experiment, our second objective of the lesson. The third objective of the lesson was we were supposed to measure the rate of transpiration using a potometer. And so I'd request the producer to display that experiment on your screens. No, that one should be displayed on the screens. A potometer is an instrument that we use in the laboratory to measure the rate of water loss. The rate of water absorption by a plant. And this is how it looks like. To some of us, this potometer is already in our laboratories, and say maybe we have performed these experiments live on. And to some of us, we do not have the potometer, but for those who do biology at advanced levels, still you'll have to do this physically. In the laboratory. So that is how a potometer looks like. This is just a diagrammatic presentation. The potometer has the following parts. It has a reservoir. That reservoir, it's where we put water, and water, this experiment it depends on water. It is airtight, but there should be enough and sufficient water. So that's why we're having a reservoir. That is where our water is always. In any case, we need water. We just open the tap and the water drips out of the reservoir to come and help in our experiment. Then we also have what you call a capillary tube. And the capillary tube is always graduated, as you can see. Then we have the volume scale, the beaker with water, and then we have the other part of a plant, a part of the potometer where we're having the cut chute. So in this experiment to measure the rate of transpiration using a potometer, it operates on an assumption that the rate of water uptake by the plant is equal to the rate of water loss by the plant, of which we know water loss by the plant into the atmosphere is what you call a transpiration. So basically in biology, we use this experiment to measure the rate of water absorption by the plant, which we know later on we can assume that the rate of water absorption will be equal to the rate of water loss, which is our rate of transpiration. So it is an assumptive experiment that bases on that basic assumption. So what happens during this experiment? One, we get a leafy shoot. As you're seeing, we have a cut shoot. Then you cut it, but when you're cutting it, you cut it underwater from its plant. Here you're not using a plant, but you're cutting a shoot or a branch from a plant. When you're cutting it, I said you cut it underwater. Why do we cut it underwater? Because if you cut it just from a branch and then you bring it to your potometer, when you've already cut it, air is going to enter into the xylem vessels of the cut shoot, and it will block that xylem vessel. And remember, it's the xylem vessel that takes up water. If we all still remember our senior 1 information, the xylem is responsible for the transportation of water and mineral salts in a plant. So when we are cutting the shoot, we cut it underwater to prevent air bubbles from entering the xylem vessel and blocking it. So when we cut it underwater, delicately we bring it underwater, and then we insert it into that place where you're seeing where it is inserted. And it is inserted in water, actually, and then it is sealed off with Vaseline or Coke and Vaseline. Then after that, we make our system airtight. There must be no air there. And then we also make our system watertight. We put a lot of water into the reservoir and make it filled with water. At the bottom, we put a beaker where water can easily drip in any case. the water is excess. After we've done that, we've fixed our plant in a potometer. In that setup, we introduce an air bubble at the end of the capillary tube. Only one air bubble is introduced at a time. So there should be many air bubbles. So when the air bubble is introduced, it should be introduced to the mark of 0 always before the experiment starts. And then you put the experiment, the apparatus, in any environmental condition you want. You can put it in wind, you can put it in sunlight, you can put it in humid air or still air to just compare the rate of transpiration in the different conditions of the environment, as we saw later on. So, as the plant up, the leaves of the plant, the leafy shoot you put, lose water. When you put it in sunlight, sunlight will strike the leaves of the plant. The leaves will lose water by transpiration to the external environment. As they lose water, they are going to create a column of what you call a pool, whereby water will be forced to move into the plant to go and replace the lost water, by the water that was lost by transpiration. So because of that pool, water will move through the capillary tube and then to enter into the stem of the plant through the xylem to replace the water that is being lost. And because of that, the air bubble will keep on moving at a slower pace towards the leafy, across the capillary tube, as the water is being absorbed by the leafy or the cut shoot. So we say the rate of movement of the air bubble is equal to the rate at which water is being absorbed by the leafy shoot or by the cut shoot. If the cut shoot is taking up more water or faster, the bubble will move faster. If the cut shoot is taking up water at smaller intervals, then the bubble will move at a slower pace. So we operated an assumption that the amount of water that is being lost by the leaves of the cut shoot is equal to the amount of water this shoot is taking up in it. And it is equal to the rate at which the bubble is moving across the capillary tube. The bubble moves because there is a stream of water, there's that column of water that is created to draw water towards the leafy shoot to replace the one that is being lost. So to calculate the rate of transpiration there on this experiment, we use a formula that transpiration will be equal to distance moved by the air bubble divided by the time taken for that bubble to move. That is our assumption of rate of transpiration. Remember, when I was starting this experiment, I told you that we operate this experiment on an assumption that the rate of transpiration is equal to the rate of the amount of water absorbed by the plant, by the cut shoot. So we also take it, the producer should display it again on your screen. So we also take it that the amount of water that is being lost from the leaves of this shoot when it is exposed to sunlight will be equal to the amount of water that is being drawn into the shoot of the plant across the capillary tube. And that is the rate at which the bubble is going to move, because the bubble is pulled by the water flowing towards the shoot to replace the lost water. And that is how we calculate the rate of transpiration. We can do this experiment in windy environment, we can do it in sunlight, we can do it in still air, we can do it in under the different environmental conditions that affect the rate of transpiration. And then we see under which environmental condition is the bubble moving faster than the other. However, there are many precautions that should be followed when carrying out this experiment. The majority of people who carry out this experiment, in most cases, end up not getting end results, or they end up not seeing their bubble move, and they keep on asking, what is happening to my potometer? So some of these precautions should be followed. One, when you are cutting, when you're getting a shoot to use here, the shoot should be having very many leaves. Why should it have very many leaves? So that there's significant water loss from the leaves that is going to draw water into the shoot of the plant to move this air bubble. If you get a shoot that is having like 1 leaf or 2, the amount of water lost through that leaf is almost negligible to create a significant pool of water into the shoot. And thus you will see your bubble remain static almost the entire day. So you have to get a twig that has very many leaves so that you increase the rate of water loss or surface area over which transpiration is taking place over the leaves, so that more water is being lost from the plant, creating that pool to take up water in order for your air bubble to move. Then the other thing I said, another precaution is your leafy shoot should be cut underwater, not in air. You don't cut a branch and then you come with it to insert it in your potometer. No, by the time you bring it, air would have entered the xylem vessels and would have broke the xylem vessels. So you cut it underwater and you bring it underwater and fix it in the potometer when it's underwater. Why? We prevent blocking of the xylem vessel, because if the xylem vessels are blocked, then water will not move even in this potometer. Why? Because it's the xylem responsible for the movement of water up the shoot. So if however much the shoot loses, the leaves lose water by transpiration, when the xylem is blocked, water will not flow through our capillary tube to enter the stem or to enter the shoot, and then you have your bubble static and you not have end results produced. The next precaution is you should only have a single air bubble introduced at a time. To some people, many air bubbles are introduced here, and then you get confused on which air bubble you're following. And then they start moving at different paces and you're not sure of which one is moving. You will get results that are not reliable. So to get reliable results, you only use one bubble at a time. Then always, after investigating the rate of transpiration in sunlight and you're taking it now into another condition, environmental condition, you must reset the air bubble. If it had already moved, say, a distance of around 10 centimeters per minute, or maybe per 30 minutes, then you must reset the air bubble to come back to the 0 mark before you investigate the rate of transpiration in another environmental condition. The capillary tube you use must be graduated and transparent enough for you to see the air bubble moving. So it should be, in most cases, the capillary tube is colorless and it is graduated. The graduations come with it so that you can easily measure the distance this air bubble is moving and calculate your rate of water uptake or rate of transpiration. So that is how we measure the rate of transpiration using this instrument we call a potometer. I said the potometer is an instrument we find in our laboratories, and we just find it intact the way it is. Your only purpose is to input their water and also introduce there your plant, and then introduce an air bubble. And that air bubble, you just monitor the distance moved by the air bubble over a particular time interval with an assumption that as the air bubble is moving, it's showing that water is being drawn through the capillary to go and enter the shoot. And that means the leafy shoot is absorbing water, and with an assumption that the water that is being absorbed by the leafy shoot is equal to the amount of water that is being lost by the leaves by transpiration. So it's still an assumptive experiment that we base on to measure the rate of transpiration. And then lastly, our summary for today, we are going to look at how plants that are located in desert environments, those plants, we call them xerophytes. Adaptations of xerophytes to reduce the rate of transpiration. Remember, in the last lesson I said transpiration is a necessary evil. Why? The plant needs it, but if it exceeds its normal, then it can become harmful in a way that the plant will wilt or it will die. Because I said transpiration is very essential in helping the plant to take up water that has been absorbed from the soil, water uptake, or uptake of absorbed water from the soil. But then if the rate at which the plant is losing water to the environment exceeds the rate at which the plant absorbs water, then there is danger. It means that the plant is losing more water than it's getting, and then the plant will start wilting. At the end of the day, it will die. So this is a challenge that is faced by many plants, particularly plants that grow in desert environments. Desert environments, I would request the producer to show the desert environments and the plants that grow there for us to be at par with the lesson. So for the plants that grow in desert environments, and because in a desert environment, next please, because in a desert environment, the soil is dry, that one. The soil is very dry, and as that the amount of water in the last one, the previous one, and as such that one, and as such the amount of water that is being lost out of the plant is higher than the amount of water that plant is getting. So the plant is bound to undergo what you call wilting. Wilting because it is losing much water than it is gaining from the soil. So as such, there is some deficit here. So that is a desert environment, and some of the plants you can see that grow in desert environment, actually they are not very big trees. You find them they are not normal. They have their own unique kind of characteristics. The amount of water in that soil is very low. Remember, it's a desert, and so there's a lot of sunlight. You know the desert countries we have. One of them is the United Arab Emirates. Those are parts of the Middle East countries. So there's a lot of sunlight, but there is less, and then there is less water in the soil. And when there's a lot of sunlight, the plant is going to be hit by a lot of heat, and the water in that plant will easily change into vapor, and the plant can easily lose water to the external environment. So the rate of water loss in a desert by a plant is higher than the rate at which that plant gains water. And as such, those plants are called xerophytes, or desert plants. They have developed particular unique features on them that enable them to survive in deserts or in desert environment without dying or without wilting, irrespective of very little water they are growing in and very large amounts of water they are losing. So some of the adaptations, the producer should be showing the different desert plants I'm going to talk about. Some of the adaptations that desert plants have gotten to reduce the rate of transpiration is most of them have their leaves reduced into thorns or spines. This is common in cactus. For those who know cactus, the producer kindly show the different plants that have thorny structures onto the screens. So instead of the plant having the normal leaf that we see in our plants here in the normal tropic environment, that one, the plant will have a very thick and succulent stem, but then it will have a lot of thorns coming out. When you look at those thorns or spines, we think they are just protective. Yes, they are protective, but in some plants, those thorns are the leaves of the plants. And what you're seeing, the green thing, the green stuff you're seeing there is the stem. So the leaves are reduced into thorns or spines in order to reduce the rate at which the rate of transpiration. You reduce the surface area over which that leaf is losing water to the external environment. There are very many other thorny plants. The producer, I would request you keep on posting the different thorny plants that are in the images you have to the screens for people to see. So apart from the plants having their leaves reduced to thorns and spines, the leaves also of those plants in desert plants are reduced in size. They are very small. You can show that one. They are very small in size. That is another plant. It has a very thick stem, but the thorns that are coming out are the leaves. Then what you're seeing heavy is the stem. It's also an example of a desert plant. So the thorns are the leaves, and the stem is the thick one. Then that one there can show it out. This one is now basically, this is a common plant. We call it what? Aloe vera? But you can see that it is thorny in nature. And the thorns are meant to lower the surface area over which water is being lost to the external environment. Now, the other adaptation of this particular plant you're seeing is the leaves are very thick. And the thickness is, they are thick and succulent, that they store water in them. That even when the place where they are growing is very dry, they cannot easily lose water to the external environment because they're having a lot of water stored in them. So that is another adaptation, possession of thick and succulent leaves and stems to store water. The other adaptation is the shade of their leaves. There's that one again, it's another thorny plant and a thick stem that you're seeing. So all those are adaptations for reducing transpiration. I would request the producer to keep on posting the different pictures on screens as I'm explaining. Then the other adaptation is most of those plants have their leaves reduced in size. The size of their leaves is very small. Instead of them having the large size leaves as usual, you find them having small leaves. And the small leaves are meant to reduce the surface area over which transpiration is taking place, because a large sized leaf will have a larger surface over which water is being lost than a small sized leaf. And then the other adaptation is leaf rolling. Show it on the screen. Show that picture on the screen, rolling of the leaves. Yeah, some plants, that one, some plants will roll their leaves in order to reduce the rate at which water is being lost across the entire surface of the leaf. So they will roll the leaf, and in the process of rolling, they are capturing a lot of moisture and humid air around them, and that one reduces the rate of transpiration between the leaf and the external environment. Then the other one is some trees will shed off their leaves. Request the producer to show trees that have shaded off their leaves, like in a dry environment. Even here in Uganda, when it's like in December, January, when it's very, very dry, the trees will start shedding off most of their leaves. Not because they don't want them, the leaves will dry out, and when they dry out, they will fall off and the tree will remain with fewer leaves. That is that one. That is another adaptation of lowering the rate of transpiration. That one should be displayed on the screens. So that is another adaptation of lowering the rate of transpiration. So when you find them, when they are shedding off their leaves, they will shed them off to reduce the surface area over which they are losing water. And then when it becomes a rainy season again, they will regain their leaves. So it's an adaptation. The next adaptation is some of these plants get what you call deep sunken stomatas, or stomatas as I call them. So the stomatas are located in deeper pits. The producer has that picture. I'd request him to put it on screen for you to see the sunken stomatas. So they would be located in deeper ends of the plant. And then when they are there, that one should be displayed. When they are located, you can see that is a leaf. It is rolled, it has hairs, and then the stomata is it is sunk inside, innermost of the leaf. And that one also reduces the rate at which, by the time water moves out of that pit of a sunk stomata to the external environment, or by the time sunlight hits that pit, it will take a longer time. So that one also is done by plants to reduce the rate of transpiration. Some plants have hairy laminas. The producer has that picture, can show you a leaf with a hairy lamina. And the hairs are just meant to also trap some humid air around the leaf. Yeah, that one should be exposed. Those are the hairs on the leaf, and that is the lamina. So the hairs just lower the surface area over which water is being lost, because the hairs make the leaf appear to be more thick. And when it is thick, the diffusion distance of water from within the leaf to the external environment is going to increase. So it will take longer for water to be lost from that leaf to the external environment. So I think there are very many other points. And then the other unique point, which is physiological, is some leaves will undergo what you call a reversed stomatorhythm opening mechanism. What is a reverse rhythm opening mechanism? Here, instead of the stomaters opening during daytime, they open at night and they close during daytime. And remember, the highest amount of transpiration occurs through the stomaters. So during daytime, when there's a lot of sunlight, there's a lot of latent heat, they are closed. So water cannot easily get its way out of the leaf. And in the night, when it is still cold and it's still, then they open. And that one reduces the rate at which transpiration takes place. It's very common in the calm plants. So those are some of the adaptations of xerophytes to reduce the rate of transpiration, or desert plants. As we saw, the desert plants include the cactus, we have the acacia, we have the euphorbias. As you've seen the different plants, all the plants that have been shown are desert plants, and they're capable of growing in deserts. I don't have much to tell you today. That is what I wanted to tell you today about transpiration. I have summed it up today, and the next time I come here, we are going to look at coordination, and as I said, coordination in animals. So for today, what have we looked at? In summary, we've looked at the experiment to show that transpiration occurs majorly in leaves. We've looked at an experiment to compare the rate of transpiration on the upper and the lower surface of the leaf. We've looked at an experiment to measure the rate of transpiration using a potometer. And then we've looked at how desert plants are adapted to reduce the rate of transpiration. And as I said earlier on, the reference questions, I left 2, but I said there are very many reference questions. The first question is question 35, 2014, paper 1, and question 36, 2008, paper 1. Those are the reference questions for today's lesson. The next time, we shall look at coordination. Thank you so much for tuning in to study biology with me. I am so humbled for God and my country.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne bw'osomeseza omwana wo mu masomero ga Giant Schools omuli kampasi y'e Bombo Kalule n'ey'e Kabalagala toba na bweraliikirivu bwonna